where warmth begins to fade. If you could drift outward from Earth tonight, leaving behind the familiar glow of city lights and the comforting warmth of the sun, you would begin to notice something subtle at first. The light would not disappear suddenly. It would thin, it would soften, it would lose its intensity. And as you moved farther and farther away, warmth itself would begin to feel like a memory. Our story begins at that boundary. The place where sunlight grows faint and cold begins to dominate. Here, at the outer frontier of our solar system, lie two worlds shaped by distance, Neptune and Pluto. To understand how far they truly are, we must first understand how we measure distance in space. Astronomers use something called an astronomical unit, or AU. One astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers. At that distance, sunlight feels strong. It powers oceans, winds, forests, and life itself. But sunlight does not remain constant as you travel outward. It weakens, and it weakens quickly. The intensity of sunlight follows a simple mathematical rule. It decreases with the square of the distance. If you move twice as far from the sun, the light becomes 4 times weaker. 3 times as far, and it becomes 9 times weaker. By the time you reach Neptune, orbiting at an average distance of about 30 astronomical units, sunlight is no longer warm and bright. It is faint, nearly 900 times weaker than what we experience on Earth. Imagine standing under a midday sky where the sun shines like a brilliant star rather than a blazing disk. The light would feel more like a deep twilight than true day. Shadows would still exist, but they would be soft, subtle, quiet. Now continue outward, past Neptune's orbit, past the final giant planet, drifting into the region known as the Kuiper Belt. Here, around 39 astronomical units on average, Pluto follows its elongated path around the Sun. At this distance, sunlight is roughly 1,500 times weaker than on Earth. The Sun would appear small, still bright, still unmistakable, but no longer overwhelming. And warmth, as we know it, would be gone. Distance in the outer solar system is difficult for the human mind to grasp. If Earth were placed 1 meter from the Sun in a scale model, Neptune would sit 30 meters away. Pluto would drift nearly 40 meters out. The space between them would feel mostly empty. But that emptiness is filled with silence, with cold, with worlds that move so slowly around the Sun that entire human lifetimes pass without them completing a single orbit. Neptune takes 165 Earth years to circle the Sun once. Pluto takes 248 years. These are not seasons we can easily imagine. They are spans of time longer than the modern history of many nations. At such distances, warmth does not vanish instantly. It fades gradually. Neptune, despite its remoteness, is not entirely frozen. In fact, it radiates more heat than it receives from the Sun. This internal warmth, left over from its formation billions of years ago, fuels its violent winds and deep atmospheric storms. But Pluto is different. Small, rocky, and icy. It cannot hold on to internal heat as efficiently. Its surface temperature averages around -220 degrees Celsius, cold enough that nitrogen, methane, and carbon monoxide freeze into solid ice. On Pluto, mountains are carved not from rock alone, but from frozen water ice that behaves like stone under such low temperatures. Yet even Pluto is not completely still. As it moves closer to the Sun along its elliptical orbit, its frozen nitrogen sublimates, turning directly from solid ice into thin gas. For a brief portion of its 248-year year, Pluto develops a fragile atmosphere. Then, As it drifts outward again, that atmosphere collapses and freezes back onto the surface. Cold at the edge of the solar system is not a simple condition. It is a dynamic balance between distance, internal heat, composition, and time. Neptune and Pluto exist at the threshold where sunlight is weak but not absent. They are far enough from the sun to feel detached from its warmth, yet close enough to remain gravitationally bound. They inhabit the frontier, not interstellar space, but the last quiet region before it begins. From Earth, both Neptune and Pluto appear as faint points of light. Neptune can just barely be glimpsed through binoculars under dark skies. Pluto requires powerful telescopes. For most of human history, neither was known. Neptune was discovered in 1846, predicted by mathematics before it was seen. Pluto was discovered in 1930, after a long search for what was once thought to be a larger, hidden planet. Today, Pluto is classified as a dwarf planet. Neptune remains the 8th and final major planet. But classification does not diminish their mystery, because both represent the far edge of our solar system's warmth. They exist where the sun's energy fades into deep cold, and they orbit in darkness that lasts decades. They experience seasons measured in generations, and yet they are not identical. Neptune is massive, 17 times the mass of Earth. Pluto is tiny by comparison, smaller than Earth's moon. Neptune is wrapped in thick hydrogen and helium clouds. Pluto is covered in nitrogen ice plains. Neptune spins in 16 hours. Pluto rotates every 6.4 Earth days. Neptune roars with winds exceeding 2,000 kilometers per hour. Pluto rests in near silence, with only faint seasonal breezes when its atmosphere briefly awakens. Distance shapes them differently. Size shapes them differently. Composition shapes them differently. But both are defined by the fading warmth of the sun. At 30 to 40 astronomical units, sunlight becomes a whisper. Heat becomes a memory. And yet, even in that cold frontier, change continues. At Neptune's storms churn. Pluto's ice flows slowly like glaciers. Gravity still binds them to the sun. Time still carries them forward. The far and frozen worlds are not lifeless relics. They are dynamic in their own quiet ways. They remind us that the solar system does not end abruptly. It transitions, from warm to cold, from bright to dim, from active and bustling to distant and silent, but not empty, never empty. As we continue this journey, we will examine how cold these worlds truly are, what temperature means at such distances, why Neptune, despite being farther than Uranus, radiates more heat, why Pluto sometimes develops an atmosphere despite its freezing surface, and how distance alone does not determine everything. Because at the edge of sunlight, physics becomes subtle. Cold is not simply the absence of warmth. It is the result of balance between energy received and energy retained, between size and composition, between gravity and time. Neptune and Pluto orbit in that delicate balance. Two worlds shaped by distance. Two worlds defined by fading warmth. Neptune orbits at an average distance of about 30 astronomical units from the Sun, which places it roughly 4.5 billion kilometers away from the source of nearly all warmth in our solar system. At that distance, sunlight is no longer a powerful force shaping climate and surface conditions in obvious ways. Instead, it becomes a faint illumination, nearly 900 times weaker than what Earth receives. The Sun, viewed from Neptune's upper atmosphere, would appear small and intensely bright. But it would no longer dominate the sky with the same overwhelming brilliance we experience here. The light would resemble a strong star rather than a radiant disk filling the horizon. Yet even in this dimness, Neptune is not quiet, nor is it simple. Despite receiving so little solar energy, Neptune is astonishingly active. Its cloud-top temperatures hover around -214 degrees Celsius, placing it among the coldest planetary environments in the solar system. But temperature at the top of its atmosphere does not tell the full story. Beneath those methane-rich clouds, the planet radiates internal heat. In fact, Neptune emits more than twice the energy it receives from the Sun. This excess heat escapes from deep within, likely leftover from the planet's formation and sustained by ongoing gravitational compression and internal convection. With that internal energy is what drives the extraordinary atmospheric motion observed during Voyager 2's flyby in 1989. Neptune is often described as an ice giant, but that term can be misleading. It does not mean that Neptune is a frozen ball of ice like a distant comet. Instead, it refers to the presence of volatile compounds such as water, ammonia, and methane that were incorporated into the planet during its formation. Under the immense pressures inside Neptune, these substances do not exist as ordinary ice. They are compressed into exotic states, superheated fluids, dense conductive layers, and possibly even superionic phases, where atoms behave in ways unfamiliar to everyday experience. The interior of Neptune is therefore not cold in the same way its cloud tops are. Temperatures may rise to thousands of degrees Celsius toward the core. The presence of internal heat is what allows Neptune to maintain the fastest winds in the solar system. Supersonic jet streams circle the planet at speeds exceeding 2,000 kilometers per hour. Massive storm systems form and dissipate over time, appearing as dark spots against the deep blue atmosphere. This dynamism is surprising for a planet so far from the Sun. If solar energy were the primary driver of atmospheric motion, Neptune would be expected to appear calm and frozen. Instead, it behaves as though it carries its own internal engine, pushing heat outward through layers of gas and fluid. That engine remains one of Neptune's enduring mysteries, especially when compared to Uranus, which lies closer to the Sun yet emits far less internal heat. Neptune's size also plays a role in how it responds to distance. With a mass about 17 times that of Earth and a diameter nearly 4 times larger, Neptune possesses significant gravitational compression. That compression traps heat more effectively than smaller bodies can. Its thick atmosphere of hydrogen and helium acts as insulation, slowing the loss of internal energy into space. Over billions of years, this retained heat continues to shape the planet's behavior. In this sense, distance from the Sun does not fully determine how cold a world becomes. Internal structure and size matter just as much as sunlight. A year on Neptune lasts 165 Earth years. This means that since its discovery in 1846, Neptune has completed just one full orbit around the Sun. Seasons on Neptune last roughly 40 Earth years each. Because of its axial tilt of about 28 degrees, similar to Earth's tilt, Neptune experiences seasonal changes in sunlight distribution. However, the changes occur slowly and subtly. The faint sunlight that reaches Neptune varies slightly over decades, influencing atmospheric patterns in ways we are only beginning to understand. During Voyager 2's flyby, Neptune's southern hemisphere was in summer. Since then, the planet has gradually shifted toward a new seasonal configuration, though the process unfolds on timescales far longer than human observation typically allows. From a physical standpoint, Neptune exists in a transitional thermal regime. It is far enough from the Sun that external heating is minimal, yet large enough to sustain internal warmth. And this creates a layered environment where cloud-top temperatures are extremely cold, while deeper regions remain hot and dynamic. Methane in the upper atmosphere absorbs red light and reflects blue wavelengths, giving Neptune its vivid coloration. But beneath that blue appearance lies a complex system of convection, pressure gradients, and possibly even exotic chemistry, such as carbon crystallization under high pressure. Neptune's gravity also shapes its environment in subtle ways. The planet's mass allows it to retain a thick atmosphere despite its distance. Smaller bodies at similar distances, such as Pluto, cannot hold on to substantial atmospheres over long periods. Neptune's gravitational pull prevents most atmospheric escape, preserving the hydrogen-helium envelope that blankets the planet. This atmospheric retention contributes to its ability to trap and redistribute internal heat. In contrast, smaller icy worlds lose heat more rapidly and lack the insulation necessary for sustained atmospheric turbulence. Even the way Neptune interacts with sunlight differs from inner planets. At 30 astronomical units, solar radiation pressure is weak and solar wind interactions are diminished. Yet Neptune still possesses a magnetosphere generated by internal conductive layers. That magnetosphere interacts with the faint solar wind that reaches it, producing auroral activity and shaping charged particle environments. The existence of such magnetic phenomena at this distance further emphasizes that Neptune is not merely a frozen relic of the outer solar system. It remains electromagnetically active. In considering Neptune's distance, it becomes clear that far does not simply mean cold and inert. Distance reduces solar influence, but it does not eliminate planetary complexity. Neptune demonstrates that internal heat can compensate for weak sunlight. Its storms, magnetic field, and convective processes all arise from forces independent of direct solar energy. This makes Neptune fundamentally different from Pluto, which relies almost entirely on sunlight for atmospheric change. The faint sunlight at Neptune's orbit creates an environment of perpetual twilight, but it does not extinguish motion. Instead, it shifts the balance of energy sources. Where Earth's climate depends primarily on solar radiation, Neptune's behavior depends heavily on internal heat and gravitational dynamics. In that sense, Neptune challenges the intuitive assumption that the farther a planet lies from the Sun, the simpler and colder it must be. It is indeed cold at its cloud tops, but it is not dormant. As we move outward from Earth through the solar system, Neptune marks the final giant planet before the Kuiper Belt begins. It stands at the threshold between the classical planetary realm and the icy frontier beyond. Its distance from the Sun defines its environment. Yet its size and composition redefine what cold means in planetary terms. Neptune is not just far. It is a complex interplay between fading sunlight and persistent internal warmth. If Neptune is a distant giant sustained by hidden warmth, Pluto is something very different. Smaller, lighter, and far more vulnerable to the cold. Pluto orbits the Sun at an average distance of about 39 astronomical units. That places it nearly 6 billion kilometers from the Sun. At that distance, sunlight is about 1,500 times weaker than what Earth receives. The Sun in Pluto's sky would appear bright but small, like an intense star suspended in a black background. There would be daylight, but it would resemble a permanent twilight compared to the brightness of Earth. Pluto's orbit is not circular. It is highly elliptical, meaning its distance from the Sun changes significantly over time. At its closest point, called perihelion, Pluto comes within about 29 astronomical units of the Sun, actually closer than Neptune's average distance. At its farthest point, aphelion, it drifts nearly 49 astronomical units away. This elongated orbit creates dramatic long-term changes in temperature and atmospheric behavior. But unlike Neptune, which follows a relatively stable path, Pluto moves through cycles of slightly stronger and weaker sunlight over its 248-year year. Because Pluto is so small, only about 2,377 kilometers in diameter, smaller than Earth's moon, it cannot retain heat as effectively as Neptune. Its gravity is weak, about 1/15 that of Earth. This weak gravity means Pluto struggles to hold on to an atmosphere over long periods. Instead, its atmosphere appears and disappears depending on where it is in its orbit. When Pluto approaches perihelion and receives slightly more sunlight, surface nitrogen ice sublimates directly into gas. A thin atmosphere forms, composed mostly of nitrogen with traces of methane and carbon monoxide. As Pluto moves outward toward aphelion and temperatures drop, that atmosphere freezes and falls back to the surface like snow. Surface temperatures on Pluto average around -220 degrees Celsius. In some regions, temperatures may fall even lower. At such extremes, familiar substances behave differently. Nitrogen becomes solid ice. Methane freezes into crystalline deposits. Even carbon monoxide exists in frozen form. The ground beneath any hypothetical observer's feet would not resemble soil or rock in the way we imagine on Earth. Instead, it would be a mixture of water ice, so hard at those temperatures that it behaves like stone, and layers of volatile ices that can flow slowly like glaciers over time. The New Horizons spacecraft, which flew past Pluto in 2015, revealed a landscape that was both alien and unexpectedly complex. One of the most striking features was Sputnik Planitia, a vast, heart-shaped basin filled with nitrogen ice. This basin appears smooth and relatively young in geological terms, with polygonal patterns suggesting slow convection within the ice. Even in deep freeze, Pluto shows signs of activity. Nitrogen glaciers creep across the surface at rates far slower than Earth's glaciers, but measurable over long timescales. Mountains composed of water ice rise several kilometers high, rigid and stable in the cold. Despite its small size, Pluto may not be entirely frozen internally. Some models suggest that it could retain a subsurface ocean beneath its icy crust. The presence of large fractures and tectonic features observed by New Horizons hints at internal expansion in the past. If Pluto once had a warmer interior, perhaps from radioactive decay within its rocky core, liquid water mixed with ammonia could have persisted beneath the surface for millions or even billions of years. Ammonia acts as this anti-freeze, lowering the freezing point of water and allowing liquid layers to survive at lower temperatures. If such an ocean exists, it would be hidden beneath tens or perhaps hundreds of kilometers of ice. Unlike Neptune's superheated internal ocean, Pluto's hypothetical ocean would be cold, dark, and trapped under immense pressure from overlying ice. Yet even this possibility demonstrates that distance alone does not define a world's complexity. Pluto is small and far from the Sun, but it is not necessarily geologically dead. Pluto's axial tilt adds another layer of contrast with Neptune. Our Pluto is tilted by about 120 degrees, meaning it essentially rotates on its side relative to its orbital plane. This extreme tilt produces dramatic seasonal effects. Some regions may experience decades of continuous sunlight, followed by decades of darkness. Combined with its elliptical orbit, these long seasons cause volatile ices to migrate across the surface over centuries. Nitrogen and methane may sublimate in one hemisphere and recondense in another, slowly reshaping the planet's appearance. Unlike Neptune, Pluto does not possess a thick insulating atmosphere. Its atmosphere, when present, is tenuous. Only a few microbars of pressure at the surface. It cannot trap heat effectively. When sunlight fades, heat radiates away into space quickly. This is why Pluto's temperature responds strongly to changes in solar distance. Neptune's massive bulk buffers it against rapid temperature swings, but Pluto remains exposed to the full effect of its elongated orbit. Gravity also plays a defining role. Neptune's escape velocity is high, allowing it to retain light gases like hydrogen and helium. Pluto's escape velocity is much lower. Lighter gases escape into space over time. Only heavier molecules like nitrogen can remain temporarily bound, and even they can escape slowly through a process known as atmospheric escape. Over billions of years, Pluto has likely lost significant amounts of volatile material to space. The contrast between Neptune and Pluto begins to sharpen here. Neptune, though far, maintains internal heat and atmospheric turbulence. Pluto, even farther and much smaller, responds directly to the sun's weak influence, and on Neptune's cold is layered over warmth. Pluto's cold penetrates deep into its structure. Neptune's winds rage. Pluto's air, when present, drifts gently across frozen plains. Neptune's magnetosphere shields its atmosphere. Pluto lacks a global magnetic field entirely. Yet Pluto is not merely a frozen relic. Its orbit is locked in a 3-to-2 resonance with Neptune, ensuring that despite crossing Neptune's orbital path, the two never collide. This gravitational dance reveals that even at great distances, structure and order govern motion. Pluto's existence in the Kuiper Belt places it among countless icy bodies shaped by Neptune's gravity. It is both independent and influenced, small but not insignificant. Pluto's moons also reflect its uniqueness. The largest moon, Charon, is so large relative to Pluto that the two form a binary system, and they orbit a common center of mass located outside Pluto itself. This gravitational pairing further distinguishes Pluto from Neptune. Neptune dominates its moons completely. Pluto shares dominance with Charon. This subtle detail reminds us that scale matters profoundly in planetary systems. If you could stand on Pluto's surface during perihelion, you might witness a faint blue haze in the sky, created by sunlight scattering through nitrogen gas. If you remained there for decades as Pluto drifted outward, that haze would fade, the atmosphere would collapse, and snow would fall silently back to the ground. Temperatures would drop further. The sun would shrink slightly in apparent size. The cold would deepen. Pluto embodies what happens when a small world ventures to the edge of sunlight without the mass to sustain internal warmth. Its frozen plains, thin atmosphere, and glacial flows represent the delicate balance between solar heating and radiative cooling. Where Neptune carries its own internal energy, Pluto relies almost entirely on the distant sun. Together, Neptune and Pluto illustrate two different responses to distance. Neptune defies expectations by remaining dynamic despite weak sunlight. Pluto exemplifies the vulnerability of small bodies to deep freeze, yet surprises us with subtle geological activity. Far from the sun, size and structure become as important as distance itself. When we say that Neptune orbits at 30 astronomical units and Pluto at an average of 39, the numbers can begin to blur. 30, 39. They sound close together, almost modest. But in the outer solar system, a difference of 9 astronomical units is enormous. After 1 astronomical unit equals roughly 150 million kilometers. That means Pluto's average distance from the Sun is more than 1.3 billion kilometers farther out than Neptune's. In human terms, that gap alone is nearly 9 times the distance between Earth and the Sun. Distance in space is deceptive because it lacks familiar reference points. On Earth, we measure separation in kilometers and feel it through time. How long it takes to drive somewhere, to fly across an ocean. In the outer solar system, The scale expands beyond instinct. Light itself becomes our measuring tool. Sunlight takes about 8 minutes to reach Earth. It takes about 4 hours to reach Neptune. And at Pluto's average distance, sunlight travels for nearly 5.5 hours before arriving. By the time sunlight touches Pluto's frozen plains, and it has already left the sun long before most of Earth's morning routines begin. This delay in light is not merely poetic. It reflects energy dispersion. As light spreads outward in all directions, its intensity weakens according to the inverse square law. At Neptune's orbit, the sun's energy is diluted to roughly 1/900th of what Earth receives. At Pluto's average orbit, it is reduced to about 1/15%. The sun's power does not disappear. It spreads thinly across a vast sphere of space. Neptune and Pluto exist in the outermost regions of that sphere where warmth is scarce and fragile. Communication across these distances becomes a matter of patience. If a spacecraft orbiting Neptune sends a signal to Earth, that signal requires about 4 hours to arrive. A reply takes another 4 hours. A single exchange spans nearly 8 hours. For Pluto, the delay grows even longer. New Horizons, during its flyby of Pluto in 2015, transmitted data across billions of kilometers. Each signal required more than 4.5 hours to reach Earth. And because its data rate was limited by distance, it took over a year for all of Pluto's information to be downloaded fully. This vast separation also means the gravitational influence weakens with distance from the Sun. The Sun's grip remains dominant, but the orbital speeds of distant worlds slow dramatically. Neptune travels around the Sun at about 5.4 kilometers per second, far slower than Earth's 30 kilometers per second. Pluto moves even more slowly, averaging about 4.7 kilometers per second along its elongated orbit. The farther from the Sun, the slower the journey. Years stretch into centuries. But distance alone does not dictate experience. Neptune and Pluto do not feel the same cold simply because they are far. Their internal properties modify how they respond to that distance. Neptune's massive bulk and insulating atmosphere buffer it against rapid heat loss. Pluto's small size exposes it to deeper cooling. Yet both remain gravitationally bound within the Sun's sphere of influence. They have not drifted into interstellar space. They remain tethered by gravity, tracing vast arcs that span human history many times over. Scale models can help illustrate this immensity. If the Sun were the size of a basketball placed at one end of a football field, Earth would sit about 1 meter away. Neptune would stand 30 meters from the Sun, nearly 1/3 of the field's length. Yet Pluto would rest nearly 40 meters away. The space between Neptune and Pluto would feel empty and quiet. But in that emptiness, countless icy objects drift, Kuiper belt bodies shaped by Neptune's gravity. From Neptune's perspective, Pluto is not infinitely distant. Their orbits are linked through resonance. Pluto's 3-2 resonance with Neptune means their paths remain synchronized despite Pluto's eccentric orbit crossing Neptune's orbital distance at times. Even when Pluto ventures closer to the Sun than Neptune does, their gravitational dance prevents collision. Distance does not imply isolation. Even at billions of kilometers apart, their orbits remain mathematically intertwined. Temperature scales emphasize this difference in energy. Neptune's cloud tops sit near -214 degrees Celsius. Pluto's surface averages around -220 degrees Celsius, with slight variation depending on orbital position. Though Pluto lies farther away, the temperature difference between the two is not extreme. This surprises many people. One might expect Pluto to be vastly colder than Neptune simply because it is farther from the Sun. But Neptune's internal heat complicates the comparison. Distance reduces solar input, but internal energy partially offsets it. As Pluto approaches perihelion at 29 astronomical units, closer than Neptune's 30 astronomical units average distance, its surface warms slightly. That warming is enough to trigger sublimation of nitrogen ice. For a few decades during its long orbit, Pluto develops a thin atmosphere. During those times, Pluto is technically closer to the Sun than Neptune is. Yet Neptune remains far warmer internally because of its retained heat. This illustrates how orbital mechanics and internal structure combine to shape planetary climates. The immensity of distance also influences how we perceive time. On Neptune, a single year spans 165 Earth years. On Pluto, a year lasts 248 Earth years. Entire civilizations can rise and fall before these worlds complete a single orbit. When Neptune was discovered in 1846, it had not yet completed a full orbit since its discovery until 2011. Pluto, discovered in 1930, will not complete a full orbit since its discovery until the late 22nd century. In the outer solar system, distance stretches not only space, but time itself. Sunlight weakens, motion slows, and change unfolds gradually. Our Neptune and Pluto inhabit this slow realm where events are measured not in years, but in generations. Their distance from the Sun defines a different rhythm of existence. To imagine standing on Neptune's cloud tops is to imagine dim daylight and violent winds fueled by hidden warmth. To imagine standing on Pluto's surface is to picture faint sunlight casting long shadows across frozen nitrogen plains. In both cases, the Sun remains visible. It has not disappeared. But its dominance has softened. Its warmth has faded. And yet, even at these distances, the solar system does not dissolve into chaos. Gravity maintains order. Resonance locks orbits into predictable cycles. Light still travels outward, even if faint. The far and frozen worlds are distant, but they are not detached. When we describe Neptune and Pluto as frozen worlds, we are speaking from a human perspective. On Earth, cold is something we feel. It is the bite of winter air or the chill of ice against skin. But in the outer solar system, cold is not a sensation. It is a measurement of energy. It is the absence of molecular motion compared to warmer environments. To understand Neptune and Pluto properly, we must think not in terms of comfort, but in terms of physics. Temperature is a measure of how fast atoms and molecules move. The higher the temperature, the faster they vibrate. The lower the temperature, the slower they move. At absolute zero, minus 273.15 degrees Celsius, molecular motion would theoretically stop entirely. Neptune and Pluto exist not far above that boundary. Neptune's upper cloud tops average around minus 214 degrees Celsius. Pluto's surface averages around minus 220 degrees Celsius. Both are extremely cold by terrestrial standards. Steel becomes brittle. Gases condense into solids. Chemical reactions slow dramatically. Yet even here, temperature is not uniform. On Neptune, cold exists at the cloud tops, but deeper layers grow warmer rapidly due to internal heat. The planet radiates roughly 2.6 times more energy than it receives from the Sun. This internal heat creates convection, warm material rising, cool material sinking. That movement drives Neptune's extreme winds and storm systems. Cold, in Neptune's case, is a thin outer skin overlaying a far more energetic interior. Pluto, by contrast, lacks such a powerful internal engine. Its small mass means it cooled more efficiently over billions of years. Its surface temperature reflects a near balance between the weak sunlight it receives and the heat it radiates back into space. Pluto does not have thick layers of hydrogen and helium to trap warmth. When the sun's energy fades, Pluto cools quickly. But even Pluto's cold is dynamic. As Pluto approaches perihelion, sunlight increases slightly. That modest increase is enough to sublimate nitrogen ice directly into gas. Nitrogen glaciers release vapor. A thin atmosphere forms. Temperatures may rise a few degrees, just enough to alter surface conditions. When Pluto moves outward again, that atmosphere collapses and freezes. Snow falls back onto the plains. Cold, then, is not static. It changes with orbit, composition, and internal structure. Another important distinction lies in the type of material each world contains. Neptune's atmosphere is primarily hydrogen and helium with traces of methane. These gases behave differently under pressure and temperature extremes. Methane absorbs red light, reflecting blue wavelengths and giving Neptune its deep azure color. But methane also condenses into clouds under cold conditions in the upper atmosphere. Pluto's surface materials are heavier molecules: nitrogen, methane, carbon monoxide, and water ice. At Pluto's temperatures, nitrogen behaves like ice rock. Methane forms crystalline layers. Water ice becomes as hard as granite. What we consider volatile gases on Earth become structural materials on Pluto. Pressure also influences how cold manifests. Neptune's cloud top pressures are low compared to Earth's surface pressure, but deeper in its atmosphere, pressure rises enormously. With increasing pressure, the gases compress and heat up. This means that while the upper atmosphere is cold, the interior grows hotter despite the planet's distance from the Sun. Pluto's surface pressure, when it has an atmosphere, is only a few microbars, hundreds of thousands of times thinner than Earth's atmosphere. With so little pressure to trap heat, Pluto radiates energy efficiently into space. That efficiency contributes to its extremely low surface temperatures. The concept of equilibrium temperature helps explain this balance. A planet reaches equilibrium when the energy it absorbs equals the energy it emits. Neptune absorbs faint sunlight, but emits both solar energy and internal heat. Pluto absorbs weak sunlight and emits nearly all of it back into space with little internal contribution. Interestingly, Pluto is not always colder than Neptune. Because Neptune radiates internal heat, some layers of its atmosphere are warmer than Pluto's surface, despite Neptune being closer to the Sun. Meanwhile, Pluto's surface temperature varies depending on its orbital position. When Pluto is near perihelion, it can receive nearly the same solar energy per square meter as Neptune does at aphelion. Yet Neptune remains energetically active due to its internal heat source. This reveals something profound. Distance from the Sun is not the only determinant of cold. Size matters. Composition matters. Atmospheric thickness matters. Internal energy matters. In deep space, sunlight spreads thinly. But internal heat can persist for billions of years in massive planets. Neptune likely retains heat from its formation, the gravitational energy released as material collapsed into a dense sphere. And that energy leaks outward slowly, sustaining atmospheric motion. Pluto formed from similar primordial materials, but its smaller mass meant it lost heat more quickly. Over time, its interior cooled. If a subsurface ocean exists, it may persist only because of radioactive decay within its rocky core or antifreeze-like compounds mixed with water. Cold also affects chemical behavior. On Pluto, methane can condense and freeze onto high-altitude regions. Nitrogen glaciers flow slowly across Sputnik Planitia, driven by subtle temperature gradients. On Neptune, methane condenses into clouds that participate in storm systems powered by convection. Even the concept of ice differs between the two worlds. On Earth, ice typically means frozen water. On Pluto, nitrogen ice dominates certain regions. On Neptune, the water may exist in superheated high-pressure forms deep within the planet, far from the frigid upper atmosphere. The sun at these distances provides little warmth, but still defines the outer boundary of habitability. Beyond Pluto lies even colder territory, the Kuiper belt extending outward and eventually the Oort cloud. Temperatures drop further, sunlight fades further, and orbital periods stretch into millennia. Neptune and Pluto occupy a transitional zone. They are far enough to experience deep freeze, yet close enough to retain subtle solar influence. Their cold is not absolute. It is relative, balanced between weak sunlight and internal physics. If you could measure temperature not in Celsius, but in energy flux, you would see how delicate the equilibrium becomes at 30 to 40 astronomical units. A slight shift in solar output would alter Pluto's atmospheric cycles. A gradual loss of internal heat would eventually calm Neptune's storms. Cold, at the edge of the solar system, is not merely emptiness. It is the result of intricate energy bookkeeping. Every photon that arrives from the sun counts. Every joule of internal heat matters. Neptune's cold masks hidden warmth. Pluto's cold defines its surface identity. Both exist in a realm where sunlight has diminished, but not disappeared. Both illustrate that temperature is more than a number. It is a story of balance across billions of kilometers. At first glance, the answer seems obvious. Pluto is farther from the sun than Neptune. It receives less sunlight. It must therefore be colder. But in the outer solar system, simple logic often gives way to deeper physics. To determine which world is truly colder, we must ask a more precise question. Colder where? Neptune does not have a solid surface like Pluto. Its visible surface is simply the top of its cloud layer. Those cloud tops average around -214 degrees Celsius. Pluto's surface averages around -220 degrees Celsius. By that measurement, Pluto is slightly colder. But that comparison is incomplete. Neptune's cloud top temperature reflects only a thin outer layer of a massive planet. Just beneath those clouds, temperatures begin to rise. As pressure increases, gases compress and warm. Deeper still, internal heat becomes dominant. Neptune's core temperature may reach thousands of degrees Celsius. Pluto has no such deep, sustained internal furnace. So if we compare uppermost layers, Pluto wins in coldness. If we compare interiors, our Neptune is far warmer. Yet even at the top of Neptune's atmosphere, the story is not straightforward. Neptune radiates about 2.6 times more energy than it receives from the sun. That internal energy influences atmospheric structure. It drives convection. It prevents the upper atmosphere from cooling even further. Uranus, Neptune's neighboring ice giant, emits almost no excess internal heat. Interestingly, Uranus has slightly colder cloud tops than Neptune, even though it is closer to the sun. This suggests that internal heat can significantly affect atmospheric temperature, sometimes more than solar distance alone. Pluto, on the other hand, relies almost entirely on sunlight for warming. When it drifts outward in its orbit, its temperature drops further. When it moves inward, its temperature rises slightly. During perihelion, Pluto can actually receive nearly the same solar flux that Neptune does when Neptune is at its farthest orbital point. But because Pluto lacks a thick insulating atmosphere and substantial internal heat, its surface temperature remains lower. Another factor complicates the comparison: albedo. Albedo is a measure of how much sunlight a surface reflects. Pluto has a relatively high albedo in certain regions, particularly in Sputnik Planitia, where nitrogen ice reflects significant sunlight. Neptune, by contrast, absorbs more solar energy in its methane-rich atmosphere. A high albedo means more sunlight is reflected away rather than absorbed. Pluto's reflective surface limits how much solar energy it retains. Neptune's darker atmospheric layers absorb some energy, though it remains faint overall, while pressure also influences temperature behavior. On Pluto, surface pressure when an atmosphere exists is extremely low, only microbars. With such thin air, heat escapes rapidly. On Neptune, even at the cloud tops, pressure is far greater than Pluto's surface pressure. That thicker atmospheric structure affects how energy is transported and retained. If we consider effective temperature, the theoretical temperature a body would have based purely on absorbed sunlight, Pluto and Neptune are relatively close in value. However, Neptune's internal heat raises its effective temperature above what solar heating alone would predict. Pluto has no such enhancement. In absolute terms, Pluto's surface is colder than Neptune's cloud tops by a few degrees on average. But that difference is modest compared to what intuition might suggest. One might expect Pluto to be dramatically colder simply because it is farther from the Sun. Instead, the difference is surprisingly small. Why? Because sunlight at those distances is already so weak that additional distance changes relatively little in practical terms. When sunlight is already reduced to 1/900th at Neptune, reducing it further to 1/1500th at Pluto does not double the cold. The temperature relationship is not linear. Temperature scales with the fourth root of absorbed energy due to blackbody radiation physics. This means that even large decreases in solar flux produce smaller proportional decreases in temperature. By the time you reach Neptune's distance, the curve has flattened significantly. In simpler terms, once you are very far from the Sun, going a little farther does not change temperature as dramatically as moving outward from Earth to Mars would. Another subtlety involves seasonal variation. Pluto's eccentric orbit causes larger fluctuations in received sunlight than Neptune experiences. During perihelion, Pluto warms enough to support a thin atmosphere. During aphelion, it becomes colder, and that atmosphere freezes. Neptune's nearly circular orbit results in more stable solar input over time. Which world, then, is truly colder? If you stood on Pluto's surface, you would feel temperatures near -220 degrees Celsius. If you could somehow float at Neptune's cloud tops, you would encounter temperatures around -214 degrees Celsius. By that comparison, Pluto holds the title. But the difference is not vast. If you could descend beneath Neptune's clouds, temperatures would rise rapidly. On Pluto, descending below the surface would not bring you into a hot, gaseous envelope. It might bring you into slightly warmer ice or, possibly, into a subsurface ocean, but nowhere near the temperatures inside Neptune. The comparison reveals something profound. Cold at the edge of the solar system has limits. It is shaped by physics, not just distance. Neptune's internal heat prevents it from becoming as cold as it otherwise would be. Pluto's small size prevents it from retaining similar warmth, yet both remain within a relatively narrow band of extreme cold defined by weak solar radiation. In the end, Pluto is colder at its surface. Neptune is warmer overall due to its interior. But both exist in a regime where the Sun is faint and energy flows are minimal. This subtlety challenges our assumptions. Distance alone does not determine temperature. Mass matters. Atmospheric composition matters. Orbital shape matters. Internal heat matters. Neptune and Pluto teach us that cold is not a simple gradient outward from the sun. It is a complex balance of energy sources and sinks, modified by planetary structure. Distance does more than lower temperature. It changes the very character of light itself. At Earth's orbit, sunlight feels powerful and immediate. It defines day and night with clarity. It casts sharp shadows. It warms skin in seconds. But at 30 to 40 astronomical units, sunlight becomes something quieter. It is still bright enough to illuminate landscapes, yet it lacks intensity. It feels thin. From Neptune's orbit, the sun would appear about 30 times smaller in diameter than it does from Earth. It would still be the brightest object in the sky by far, but it would no longer dominate the horizon with overwhelming brilliance. The sky above Neptune's cloud tops would likely appear dark even at noon, because sunlight would not scatter as strongly through its upper atmosphere as it does through Earth's thicker, dust-rich air. The sun would shine sharply against a nearly black background. At Pluto's average distance, the sun shrinks further. It becomes a brilliant star-like disk, intense but small. The light would resemble what we call twilight on Earth, though still far brighter than our moon's full illumination. Shadows would stretch long and faint across nitrogen ice plains. The contrast between light and darkness would feel muted. Everything would appear distant and subdued. Yet even this faint sunlight carries energy. Photons that left the sun more than 5 hours earlier would strike Pluto's surface and be absorbed or reflected. Some would warm nitrogen ice just enough to trigger sublimation during certain orbital phases. Others would reflect off bright regions like Sputnik Planitia, contributing to Pluto's relatively high albedo. At Neptune, photons would be absorbed by methane molecules in the upper atmosphere, contributing to the planet's deep blue appearance. Light defines temperature, but it also defines rhythm. Neptune's day lasts about 16 Earth hours. Despite its great distance, it rotates quickly. Day and night cycles occur regularly. The faint sunlight rises and falls over its cloud tops with relative speed. Storm systems evolve under dim but steady illumination. Pluto rotates much more slowly, one full rotation every 6.4 Earth days. On Pluto, day and night stretch longer, deepening the sense of slow change. Seasons amplify this effect. Neptune's axial tilt of 28 degrees creates seasons that last about 40 Earth years each. During summer in one hemisphere, slightly more sunlight reaches that side of the planet. But because sunlight is already weak, the seasonal difference is subtle compared to Earth. Pluto, with its extreme axial tilt of about 120 degrees, experiences far more dramatic seasonal shifts. Some regions can face continuous sunlight for decades, followed by decades of darkness. During long summers, nitrogen sublimates and forms temporary atmospheres. During long winters, that atmosphere freezes and falls like snow. Distance also affects solar radiation pressure and solar wind. At Neptune's orbit, the solar wind is much weaker than near Earth. Charged particles still flow outward from the sun, but their density has thinned significantly. Neptune's magnetic field interacts with this weak solar wind, producing auroras and shaping its magnetosphere. Pluto lacks a strong global magnetic field, so it interacts with the solar wind differently. When Pluto has an atmosphere, solar wind can gradually strip particles away, contributing to atmospheric escape. At such distances, the sun's gravitational influence remains strong enough to maintain orbital order. Yet, its radiant energy barely shapes the climate compared to internal physics. Neptune demonstrates how a massive planet can remain active, even under dim sunlight. Pluto demonstrates how small bodies rely almost entirely on that faint energy for atmospheric cycles. There is also psychological weight to distance. From Earth, both Neptune and Pluto appear faint and unreachable. But if one were standing there, Earth would be invisible without powerful telescopes. The inner planets would be lost in the glare of the sun. The solar system would appear compact, the outer stars more prominent. From Pluto's surface, the Milky Way would stretch vividly across a black sky, unobstructed by thick atmosphere. Even at 40 astronomical units, sunlight remains the defining energy source. It sets temperature equilibrium. It drives sublimation on Pluto. It contributes to Neptune's upper atmospheric structure. But its influence has weakened to the point where other forces, gravity, internal heat, orbital resonance, become comparatively more important. Distance reshapes dominance. Closer to the sun, radiation governs everything. Farther away, gravity and internal structure gain importance. Our Neptune stands at the threshold where internal heat competes with solar input. Pluto stands farther still, where solar influence fades into delicacy and fragility. And yet both remain bound to the same star. The sun's light, though faint, continues to reach them. It continues to define their years, 165 Earth years for Neptune, 248 for Pluto. It continues to provide just enough energy to prevent absolute stillness. Now that we understand how distance and sunlight define the outer solar system, we can look more closely at how cold physically shapes Neptune and Pluto. Because even though their temperatures are not dramatically different at the topmost layers, the way cold manifests on each world could not be more different. Neptune has no solid surface. If you descended through its atmosphere, you would first encounter high-altitude methane clouds drifting through faint blue light. As you move deeper, pressure would increase rapidly. The atmosphere would grow denser, darker, and warmer. There would be no ground to stand on, only layers of gas transitioning into supercritical fluids under extreme compression. Cold, in Neptune's case, exists only at the uppermost boundary where the atmosphere radiates heat into space. And yet, even in that frigid upper layer, Neptune is anything but still. Supersonic winds tear across the planet at speeds exceeding 2,000 kilometers per hour. Storm systems larger than Earth form and dissipate over time. The great dark spot observed by Voyager 2 in 1989 vanished within a few years. New storms have appeared since then. The cold at Neptune's cloud tops does not prevent motion. Instead, it coexists with internal heat rising from below. Pluto, by contrast, has a surface, solid, frozen, and visible. If you stood on Pluto, you would be standing on water ice as hard as granite at those temperatures. Around you would stretch plains of nitrogen ice, methane frost, and mountains rising several kilometers high. Cold on Pluto is not a thin atmospheric boundary. It defines the landscape itself. On Neptune, cold creates clouds. On Pluto, cold creates terrain. Neptune's methane condenses into cloud structures that move quickly under internal convection. Pluto's nitrogen condenses into glaciers that flow slowly over thousands or millions of years. The difference in mass and atmospheric thickness determines how cold shapes each world. Neptune's gravity traps its atmosphere. The weight of that atmosphere compresses lower layers and generating heat. Convection cells transport energy upward, driving wind systems. Cold exists at the top, but warmth rises from beneath. Neptune's visible environment is dynamic precisely because of the tension between cold space and internal heat. Pluto's weaker gravity cannot sustain such a thick atmosphere. Its air, when present, is thin and fragile. When Pluto moves farther from the sun, its atmosphere freezes and falls as snow. There are no supersonic winds sculpting the terrain. Instead, slow glacial flows and seasonal frost deposition define surface change. Another distinction lies in scale. Neptune is nearly 50,000 kilometers in diameter. Pluto is only about 2,377 kilometers across. This difference in size dramatically affects how heat is retained. Larger bodies cool more slowly. Neptune still holds residual heat from its formation 4.5 billion years ago. Pluto lost most of its early heat long ago. Even so, Pluto may not be entirely frozen internally. Evidence from New Horizons suggests tectonic features that could imply internal expansion at some point in its history. If a subsurface ocean exists, it would be insulated beneath thick layers of ice. But even that potential warmth is minor compared to Neptune's internal furnace. Cold also affects color and appearance. Neptune's blue color comes from methane absorbing red wavelengths of sunlight and scattering blue. Pluto's surface is far more varied in color. Some regions appear bright and icy. Others appear darker and reddish due to complex organic molecules called tholins, formed by radiation processing of methane and nitrogen. Radiation at such distances is weaker than near Earth. But over millions of years, it still alters surface chemistry. On Pluto, ultraviolet radiation and cosmic rays break apart molecules in the thin atmosphere, recombining them into darker organic compounds that settle onto the surface. Cold preserves these compounds for long periods. Neptune's thick atmosphere shields its deeper layers from direct radiation chemistry at the surface level. Instead, chemical processes occur within clouds and atmospheric layers driven by convection. The soundscape of these worlds would differ profoundly as well. On Neptune, deep atmospheric pressure and violent winds might produce roaring turbulence if one could somehow survive there. On Pluto, the near vacuum would make sound nearly non-existent. Even if winds moved across nitrogen plains during perihelion, and there would be little medium to carry sound. Cold shapes silence differently. On Neptune, cold coexists with motion and turbulence. On Pluto, cold reinforces stillness. And yet both worlds orbit the same sun, separated by less than 10 astronomical units on average. Their shared environment does not erase their structural differences. If you compared thermal inertia, the resistance to temperature change, you would find Neptune's atmosphere responds more slowly to external fluctuations due to internal heat. Pluto's surface, lacking thick insulation, responds more directly to changes in solar distance. Even the concept of weather differs. Neptune has active weather systems driven by internal convection. Pluto's weather, if present, is seasonal and slow, driven by sublimation and refreezing cycles rather than atmospheric circulation. And the phrase far and frozen applies to both worlds, but it manifests in two distinct ways. For Neptune, far means faint sunlight competing with internal heat. For Pluto, far means exposure to the cold with little internal compensation. Neptune's storms show that distance does not eliminate energy. Pluto's glaciers show that even extreme cold does not eliminate change. In both cases, the outer solar system is not static. It is not lifeless. It is simply operating on a different energy budget. At first glance, Neptune and Pluto appear to occupy overlapping territory. Pluto's orbit is highly elliptical, and at its closest point to the Sun, it travels inside Neptune's average orbital distance. In fact, for about 20 years out of its 248-year orbit, Pluto is actually closer to the Sun than Neptune is, and this happened most recently between 1979 and 1999. During that period, Pluto was technically the 8th planet from the Sun. And yet, despite this orbital crossing, Neptune and Pluto never collide. They cannot. The reason lies in one of the most elegant gravitational relationships in the solar system: orbital resonance. Pluto is locked in a 3-to-2 resonance with Neptune. For every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. This precise mathematical relationship ensures that whenever Pluto reaches the point in its orbit closest to Neptune's path, Neptune is somewhere else entirely. Their motions are synchronized in such a way that close encounters are prevented indefinitely. Resonance is not accidental. It is the result of long-term gravitational interaction. Early in the solar system's history, Neptune likely migrated outward through a disk of icy debris. As it moved, its gravity perturbed the orbits of countless small bodies. Some objects were scattered outward, others were ejected entirely, but some became trapped in stable resonances. Pluto is one of those survivors. The resonance stabilizes Pluto's orbit, despite its eccentric shape and high inclination. Pluto's orbit is tilted about 17 degrees relative to the plane of the solar system. This tilt adds another layer of protection. Even when Pluto crosses Neptune's orbital distance, it does so well above or below Neptune's path. Distance and cold define these worlds, but gravity binds them together in a silent choreography. Neptune's gravitational dominance extends far beyond its visible atmosphere. It shapes the Kuiper Belt region where Pluto resides. Many other icy bodies beyond Neptune are also locked in resonances: 2-to-1, 5-to-2, and others. These objects, known as resonant trans-Neptunian objects, owe their orbital stability to Neptune's mass and motion. Without Neptune's gravitational influence, Pluto's orbit might not be stable over billions of years. It might have been ejected from the solar system or sent into the inner regions long ago. Instead, Neptune acts as both gatekeeper and protector, maintaining structure at the edge of sunlight. This gravitational dance reveals something important about distance. At 30 to 40 astronomical units, sunlight weakens dramatically. But gravity does not fade as quickly. The Sun's gravitational pull still dominates both Neptune and Pluto, and Neptune's gravity still significantly influences Pluto. Cold reduces molecular motion, but it does not reduce gravitational force. Gravity operates independently of temperature. Even in the frozen frontier, orbital mechanics remain precise and powerful. Neptune's mass, about 17 times that of Earth, gives it the strength to shape nearby space. Pluto, far smaller and lighter, cannot exert comparable influence. Instead, Pluto responds to Neptune's gravity, adjusting its path accordingly. Yet Pluto is not entirely powerless. Its large moon, Charon, forms a binary system with it. Together, Pluto and Charon orbit a common center of mass located outside Pluto itself. This unusual configuration gives Pluto a dynamic internal system even while it remains under Neptune's gravitational supervision. The resonance between Neptune and Pluto also has implications for understanding the history of the solar system. Many models suggest that the giant planets did not form exactly where they are today. Neptune may have originated closer to the Sun and migrated outward over millions of years. During that migration, it would have scattered icy bodies into new orbits. Pluto's current path may be a relic of that migration era. If Neptune had not moved outward, Pluto might not occupy its present orbit. The far and frozen worlds are therefore linked not only by distance, but by shared history. Even today, Neptune continues to shape the outer solar system. Short-period comets that occasionally enter the inner solar system often originate in the Kuiper Belt. Neptune's gravitational nudges can redirect these icy objects inward. In that way, Neptune influences even Earth's long-term environment. The resonance ensures stability, but it also demonstrates fragility, and if Neptune's orbit were altered significantly by an encounter with a massive object, for example, the resonance could break. Pluto's orbit might destabilize. Over immense timescales, such perturbations could send Pluto inward or outward. But for now, the resonance remains firm. Neptune completes an orbit in 165 Earth years. Pluto completes one in 248 years. The ratio remains exact enough to maintain long-term order. This precision stands in contrast to the apparent emptiness and silence of the outer solar system. From a distance, Neptune and Pluto seem isolated in deep space. But invisible mathematical relationships tie them together. Even in deep freeze, even under faint sunlight, the laws of motion remain active and elegant. The gravitational dance between Neptune and Pluto reinforces the theme of this journey. Distance does not mean simplicity. Cold does not mean inactivity. The far frontier is structured. Distance from the sun does not only weaken light and lower temperature, it stretches time. On Earth, a year passes in 365 days. Seasons change within months. A child can witness dozens of summers and winters within a single lifetime. But in the outer solar system, time unfolds differently. Neptune completes one orbit around the Sun in 165 Earth years. Pluto takes 248 Earth years to complete a single revolution. This means that since Neptune was discovered in 1846, it has completed only one full orbit. Pluto, discovered in 1930, has not yet completed even one orbit since its discovery. Entire human civilizations could rise and fall before these distant worlds complete just a handful of years. Time, at 30 to 40 astronomical units, moves slowly in orbital terms. Neptune's seasons last about 40 Earth years each. Because its axial tilt is about 28 degrees, similar to Earth's, it experiences seasonal variations in sunlight. But each season spans nearly half a human lifetime. A generation could be born and grow old during a single Neptunian summer. Pluto's seasonal cycles are even more dramatic. With its extreme axial tilt of about 120 degrees, Pluto effectively rotates on its side. Combined with its elongated orbit, this creates seasons that can last over 60 Earth years. Some regions may remain in continuous sunlight for decades, while others experience prolonged darkness. Nitrogen ice migrates slowly from one hemisphere to another over centuries. In the outer solar system, seasonal change is not something one observes quickly. It is something that unfolds gradually, subtly, almost imperceptibly within a human lifespan. Cold interacts with time in powerful ways. On Pluto, nitrogen glaciers flow slowly across Sputnik Planitia. But slowly here means over thousands or millions of years. On Neptune, storm systems can form and dissipate over a few years, a relatively rapid process compared to orbital timescales, but still slow by Earth's weather standards. Time dilation in experience becomes evident when considering solar energy input. Because sunlight is faint, changes in solar output produce only modest thermal variations. Small differences in orbital position translate into subtle temperature shifts rather than dramatic swings. Pluto's elliptical orbit means it spends much of its time far from the Sun. It moves fastest when near perihelion and slowest near aphelion, according to Kepler's laws of planetary motion. During aphelion, Pluto drifts through deep cold for decades at a time. Its atmosphere, if present, collapses completely and remains frozen on the surface. Neptune's orbit is far more circular. its distance from the Sun changes only slightly during its long year. As a result, Neptune experiences more stable solar input over time. Internal heat likely plays a larger role in driving its atmospheric changes than seasonal solar variations. The rhythm of rotation also shapes perception. Neptune rotates once every 16 hours, faster than Earth. Despite its great distance, day and night cycles pass quickly. This rapid rotation contributes to its powerful jet streams and atmospheric banding. Pluto rotates far more slowly, once every 6.4 Earth days. Daylight lingers, nights stretch long. The Sun moves slowly across its sky. Shadows drift at a leisurely pace over frozen terrain. When thinking about far and frozen worlds, it is tempting to imagine them as static. But the reality is that change still occurs. It simply operates on scales unfamiliar to human intuition. A Neptunian storm observed by Voyager 2 in 1989 was gone within a few years. That may seem rapid relative to Neptune's 165-year orbit, but it still represents a slow atmospheric evolution compared to Earth's fast-moving weather systems. Pluto's glacial movements, by contrast, might take centuries to reshape landscapes. Mountains of water ice may stand unchanged for millions of years. Time and temperature are linked. Lower temperatures generally slow chemical reactions. Molecular motion decreases. Surface processes occur more gradually. On Pluto, radiation-driven chemistry produces reddish organic compounds over long timescales. On Neptune, chemical interactions occur within clouds shaped by internal convection. Even gravitational interactions unfold slowly. Pluto's resonance with Neptune has remained stable for billions of years. That stability is maintained not by rapid adjustment, but by continuous, subtle gravitational nudges that accumulate over immense spans of time. If one were to observe Neptune and Pluto from a distant vantage point, the changes would be almost imperceptible on human timescales. But over centuries and millennia, patterns emerge. Seasons shift, storms appear and fade, ice migrates, atmospheres freeze and thaw. The far edge of the solar system teaches patience. Cold slows motion, distance stretches cycles. Orbital periods extend beyond lifetimes. And yet, the solar system remains dynamic even here. Neptune circles the Sun every 165 years. Pluto takes 248. Their gravitational dance repeats with precision. The faint sunlight continues to arrive after hours of travel. Internal heat continues to leak outward from Neptune's depths. Time at the edge is slow but relentless. When we imagine the outer solar system, we picture surfaces locked in ice and darkness. We imagine cold penetrating all the way to the center of these distant worlds. But distance from the Sun does not automatically mean total internal freeze. Beneath Neptune's clouds and Pluto's frozen plains, no very different thermal stories unfold. Neptune's interior is layered and immense. Beneath its upper atmosphere of hydrogen, helium, and methane lies a deep mantle composed largely of water, ammonia, and methane in exotic high-pressure forms. These substances are not frozen solid as their names might suggest. Under extreme compression, they exist as superheated fluids. Temperatures rise dramatically with depth. At the core, estimates suggest thousands of degrees Celsius. This internal heat is partly residual energy from Neptune's formation. When the solar system formed 4.5 billion years ago, material collapsed under gravity. That collapse converted gravitational potential energy into heat. Larger bodies retained more of that heat because their greater mass slowed cooling. Neptune, with 17 times Earth's mass, has been releasing that heat slowly ever since. Gravitational compression continues to play a role. The weight of Neptune's massive atmosphere presses inward, generating additional thermal energy in the deeper layers. Convection circulates heat upward. This upward heat flow explains why Neptune emits far more energy than it receives from the Sun. Cold, therefore, defines only Neptune's outermost skin. The deeper one travels, the warmer it becomes. Pluto presents a different scenario. Its small mass, barely 0.2% that of Earth, meant it cooled far more efficiently over billions of years. It lacks the immense gravitational compression that sustains Neptune's interior heat. For a long time, scientists assumed Pluto must be completely frozen inside. However, observations from the New Horizons mission complicated that assumption. Pluto's surface shows tectonic fractures and large basins that suggest past internal expansion. One explanation is the gradual freezing of a subsurface ocean. As water freezes, it expands. That expansion could create surface cracks and faults. If Pluto once possessed enough internal heat, perhaps from radioactive decay within its rocky core, it could have sustained a liquid ocean beneath its icy crust for millions or billions of years. Ammonia mixed with water would lower the freezing point, acting as antifreeze and prolonging the existence of liquid layers. Even today, some models suggest that a subsurface ocean might persist deep beneath Pluto's crust, insulated by thick ice layers. If it exists, it would be far colder and smaller than any internal ocean inside Neptune. But it would represent a remarkable exception in such a distant world. The contrast between Neptune and Pluto underscores how mass governs thermal evolution. Larger planets cool slowly, smaller bodies cool quickly. Neptune still carries the thermal memory of its birth. Pluto may carry only faint traces. Pressure also shapes interior conditions. Neptune's internal pressures reach millions of times Earth's atmospheric pressure. Under those conditions, familiar materials behave in unfamiliar ways. Water may exist in superionic phases, where oxygen atoms form a lattice and hydrogen ions flow freely through it. Such exotic states cannot occur naturally on Pluto due to its much lower mass and pressure. On Pluto, pressure increases modestly with depth, but never approaches Neptune's extremes. Ice remains ice. Rock remains rock. Any internal ocean would exist under far milder pressures compared to Neptune's deep mantle. Despite these differences, both worlds remind us that cold surfaces do not always reflect internal conditions. Beneath Neptune's frigid clouds lies intense heat and dynamic convection. Beneath Pluto's frozen plains may lie residual warmth trapped for billions of years. Distance from the Sun shapes outer layers, but internal physics shapes cores. Another distinction involves magnetic fields. Neptune has a complex magnetic field generated by convective motion within its conductive interior layers. Pluto, in contrast, shows no evidence of a global magnetic field. Its small size and limited internal convection likely prevent the generation of a sustained dynamo. This difference reinforces the relationship between size, heat, and activity. Neptune's interior remains vigorous enough to generate magnetism. Pluto's interior, if still warm in places, is not energetic enough to sustain a similar field. Yet, even Pluto's possible ocean, if confirmed, would reveal that far and frozen does not always mean entirely lifeless or static. Warmth can persist in unexpected places, shielded by layers of insulation and slowed cooling. In the outer solar system, sunlight weakens dramatically, but planetary formation left behind internal heat reservoirs that can endure for billions of years in sufficiently massive bodies. Neptune exemplifies this endurance. Pluto demonstrates its limits. To understand how far and frozen Neptune and Pluto truly are, we must look beyond them. because neither world marks the absolute end of the solar system. Neptune orbits at about 30 astronomical units, and Pluto averages around 39. But beyond Pluto lies a vast region filled with icy remnants of planetary formation, the Kuiper Belt. This region stretches outward to roughly 50 astronomical units, and perhaps beyond, gradually thinning into what astronomers call the scattered disk. If Neptune and Pluto feel distant from the Sun, the objects beyond them experience an even deeper isolation. At 50 astronomical units, sunlight is about 2,500 times weaker than on Earth. The Sun would still appear bright in the sky, but its warmth would be nearly negligible. Temperatures in these regions approach the background chill imposed by radiative balance with space. And yet, even there, the Sun still dominates gravitationally. Neptune and Pluto exist within this transitional zone, the inner portion of the solar system's outer frontier. They are not yet in interstellar space. They are still firmly within the Sun's gravitational control. Beyond the Kuiper Belt lies the scattered disk, a region of icy bodies flung into elongated orbits by Neptune's gravity billions of years ago. Some of these objects travel hundreds of astronomical units from the Sun before returning. Farther still lies the Oort cloud, a spherical shell of icy bodies that may extend tens of thousands of astronomical units outward. Compared to those distances, Neptune and Pluto seem almost close. But temperature does not decline endlessly in a simple linear way. As one moves farther from the Sun, temperature decreases according to the balance between absorbed sunlight and emitted radiation. However, once solar input becomes extremely weak, temperature changes slow. The curve flattens. This is why Pluto, despite being farther than Neptune, is not dramatically colder by hundreds of degrees. The difference in solar energy between 30 astronomical units and 40 astronomical units is significant in flux terms, but modest in temperature terms because of the fourth root relationship between energy and temperature. In other words, once you are already extremely far from the Sun, moving a little farther does not produce a proportionally dramatic drop in temperature. This mathematical reality defines the thermal frontier where Neptune and Pluto reside. They are cold because solar energy has diminished substantially, but they are not in absolute darkness. They are not at the cosmic microwave background temperature of deep interstellar space, which sits around -270 degrees Celsius. They remain warmer than that because the Sun still reaches them. Neptune's cloud tops hover around -214 degrees Celsius, and at Pluto's surface averages around -220 degrees Celsius. Interstellar space is colder still. The difference between being within the solar system and outside it is profound. Neptune and Pluto still receive structured light from a central star. They still orbit predictably. They still participate in gravitational relationships. Even Pluto, drifting along its elongated path, remains tethered to the Sun's rhythm. Distance also affects how these worlds interact with cosmic radiation. With thinner atmospheres, Pluto's surface is more directly exposed to cosmic rays and solar ultraviolet radiation. Over millions of years, this exposure alters surface chemistry, producing complex organic compounds that darken portions of the landscape. Neptune's thick atmosphere shields its deeper layers from such radiation. Chemical reactions occur higher in the atmosphere, influenced by internal heat and methane chemistry. At the far edge of sunlight, energy becomes sparse. That scarcity slows processes. It extends timescales. It reduces volatility, but it does not eliminate structure. Neptune still commands the Kuiper Belt gravitationally. Pluto remains locked in resonance. Icy bodies beyond them drift in patterns shaped by ancient migration. the edge of the solar system is not a wall. It is a gradient, a slow fading of solar dominance into galactic background. Neptune and Pluto exist within that gradient. They are not the coldest possible places in the universe. They are not fully isolated from stellar influence. They are transitional, far from warmth, yet not entirely removed from it. If you stood on Pluto and looked outward beyond its orbit, you would see more stars than planets. The inner solar system would be invisible to the naked eye, but the sun would still shine, anchoring the sky. From Neptune's cloud tops, the Kuiper belt would lie beyond, invisible in darkness, but present as a gravitational reservoir of icy bodies. In this sense, Neptune marks the last of the major planets. Pluto marks the beginning of the dwarf planet frontier. Beyond them lies debris, fragments of formation, leftovers of migration, frozen relics of the solar system's birth. And yet, despite being so far, Neptune and Pluto are not relics. Neptune remains dynamic with storms powered by internal heat. Pluto remains geologically interesting, with evidence of glacial flow and possibly a subsurface ocean. Distance has not erased activity. It has only reshaped it. So far, we have explored Neptune and Pluto as they exist today. Far from the sun, cold but not lifeless, shaped by faint light and deep time. But the sun itself is not constant. Over billions of years, it is slowly changing. And when the sun changes, even the far and frozen worlds will feel it. The sun gradually grows brighter as it ages. Every billion years or so, its luminosity increases slightly. This is a natural part of stellar evolution. Hydrogen fuses into helium in the sun's core, altering internal pressure and energy output. The change is slow on human timescales, but relentless over cosmic ones. For Neptune and Pluto, this gradual brightening will matter. If the sun becomes even 10% brighter over the next billion years, the amount of solar energy reaching Neptune and Pluto will increase proportionally. At Earth's distance, such a change would have dramatic climatic consequences. At 30 to 40 astronomical units, the effect will be subtler, but not insignificant. On Pluto, a brighter sun would mean more sustained sublimation of nitrogen ice. Its thin atmosphere might persist for longer periods of its orbit. Seasonal changes could become more pronounced. Nitrogen glaciers might flow more actively. Regions currently locked in permanent frost might experience temporary thaw cycles measured in degrees rather than meters. Pluto's fragile balance between solid and gas depends on small differences in energy. Even modest increases in solar luminosity could alter its atmospheric behavior significantly over long timescales. Neptune's response would be different. Because Neptune's internal heat dominates its atmospheric dynamics, these solar changes would influence only the uppermost layers more strongly. Cloud patterns might shift slightly with increased solar input. Methane chemistry could adjust subtly, but Neptune's internal engine would remain the primary driver of its storms. However, far in the future, about 5 billion years from now, the sun will enter a more dramatic phase. It will exhaust the hydrogen in its core and expand into a red giant. As it expands, its outer layers will swell outward, possibly engulfing Mercury and Venus, and perhaps even Earth. During this red giant phase, the sun's luminosity will increase dramatically, hundreds or even thousands of times greater than today. When that happens, the outer solar system will warm substantially. Neptune, currently frozen at its cloud tops, may experience temperatures high enough to alter its atmospheric structure significantly. The methane that gives Neptune its blue color could break down under stronger radiation. Cloud patterns could change dramatically. Pluto would transform even more drastically. Its nitrogen and methane ices would sublimate rapidly. A thick temporary atmosphere could form. Frozen plains would thaw. Glacial flows would accelerate. Pluto, once a deep frozen world, could briefly resemble a warmer, more dynamic environment. But this transformation would not last forever. The red giant phase is temporary. Eventually, the sun will shed its outer layers and contract into a white dwarf. At that point, solar luminosity will drop sharply. The remaining stellar core will shine faintly, and the solar system will cool permanently. Neptune and Pluto will then drift through deep, lasting cold, far beyond what they experience today. Pluto's atmosphere, if present during the red giant phase, would freeze again. Neptune's internal heat would gradually diminish over trillions of years as it radiates away into space. In that distant future, both worlds will orbit a dim white dwarf star, surrounded by debris from the sun's outer layers. The solar system will no longer resemble its current structure. The far and frozen worlds we know today are not permanent in their current state. They are part of an evolving system shaped by stellar life cycles. Even now, subtle changes occur. Neptune's seasons shift slowly over decades. Pluto's atmosphere thickens and thins over centuries. These are small changes compared to the immense transformation awaiting billions of years from now. A cold, then, is temporary on cosmic scales. Warmth is temporary. Distance remains constant in orbital terms, but energy changes over time. Neptune and Pluto illustrate how planetary environments depend not only on distance and mass, but also on the long-term evolution of their parent star. The outer solar system feels static because human lifetimes are brief, but across billions of years, it is anything but still. As the sun ages, the line between far and frozen will shift outward and inward again. Neptune and Pluto will adapt in ways dictated by physics, and eventually, even they will cool into deeper silence under the faint glow of a white dwarf. When we speak of Neptune and Pluto as far and frozen, we are describing them from Earth's point of view. From here, they seem distant, dim, and almost abstract. They are points of light at the edge of a map. But perspective changes everything. If you could stand on Pluto's frozen plains and look inward toward the sun, the solar system would feel compact. The inner planets would be lost in glare. Jupiter would appear as a bright, wandering star. Saturn faint but steady. Neptune itself would be visible only through powerful instruments. Earth would be invisible to the naked eye, a pale world hidden in brightness. From that distance, the warmth of Earth would feel improbable. From Neptune's cloud tops, the sun would shine sharply but small, casting faint illumination across turbulent methane clouds. The familiar warmth of Earth would feel like a myth. The inner planets would seem crowded near the sun, tightly bound within a region of relative brightness. Distance reshapes meaning. On Earth, we think of our planet as existing within a vast solar system. But from Neptune or Pluto, Earth is the inner region, close to the star, flooded with energy. We are the anomaly of warmth. Neptune and Pluto remind us that most of the solar system is cold. Most of it receives only faint sunlight. The bright temperate region we inhabit is comparatively small. If you were to divide the solar system by volume, the majority of it lies beyond the orbit of Jupiter, in regions where sunlight is already weak. Far is relative. Frozen is relative. At 30 astronomical units, Neptune still receives enough energy to support dynamic weather. At 39 astronomical units, Pluto still receives enough to sustain seasonal atmospheric cycles. Both are far from the sun, yet still deeply connected to it. Even their gravity connects them to us. Neptune's migration long ago may have influenced the trajectory of icy bodies that eventually reached the inner solar system. Some of those bodies may have delivered water and organic molecules to early Earth. In that sense, the far and frozen frontier may have helped shape the warm and wet world we call home. Neptune and Pluto are not isolated chapters of the solar system's story. They are part of the same narrative. Neptune shapes the Kuiper Belt. Pluto reveals the diversity of icy bodies beyond the major planets. Together, they mark a boundary between classical planetary architecture and the debris of formation. When we measure their cold in degrees Celsius, we quantify only part of their reality. Cold also represents energy scarcity. It represents distance from abundance. It represents slowness of seasons, of glacial movement, of orbital motion. But it does not represent emptiness. Neptune's storms show that energy persists even under dim sunlight. Pluto's glaciers show that motion continues even at -220 degrees Celsius. Resonance shows that order remains even at billions of kilometers from the sun. Perspective reveals humility. For most of human history, Neptune and Pluto were unknown. Neptune was predicted mathematically before it was seen. Pluto was discovered only in the 20th century. Even now, we have visited Neptune only once, and Pluto only once. Entire worlds exist at the edge of sunlight, with barely a day's worth of direct observation. They remind us how much remains unexplored even within our own solar system. And yet, they are not unreachable in principle. Voyager 2 traveled to Neptune in 12 years. New Horizons reached Pluto in 9.5. Human curiosity crossed billions of kilometers of cold to glimpse these distant worlds. From Pluto, the sun still rises. From Neptune, storms still form. From Earth, telescopes still turn outward. The far and frozen worlds are not ends. They are frontiers. They show us that distance does not erase structure, that cold does not eliminate change, that even faint sunlight can sustain cycles of motion over centuries. And perhaps most importantly, they show us scale. At 30 to 40 astronomical units, the solar system feels vast. But beyond Pluto lie regions that extend tens of thousands of astronomical units outward. Compared to those distances, Neptune and Pluto are merely stepping stones. The word far loses meaning when confronted with cosmic scale. Yet within that vastness, structure persists. Neptune and Pluto orbit predictably. Their temperatures remain governed by physical laws. Their seasons unfold slowly but reliably. At the edge of warmth, physics remains constant. Cold is not chaos, it is balance. Distance is not isolation, it is perspective. And as Neptune and Pluto continue their long journeys around the sun, one orbit every 165 and 248 years, they carry on quietly, far from the center of attention, yet deeply connected to the star that defines them. The far and frozen worlds are not just about temperature. They are about understanding how energy fades, how gravity binds, and how time stretches. They are about seeing our own warm world in context. Because when you look outward to Neptune and Pluto, you begin to understand just how special it is to orbit where we do. Close enough for warmth, far enough for stability, and somewhere, billions of kilometers away, under faint sunlight, Neptune turns in blue storms, and Pluto rests in silent ice. Still bound, still orbiting, still part of the same system, far, frozen, but never truly alone. Imagine, for a moment, that you could stand safely on each of these distant worlds, not as a fragile human in a thin suit, but as an observer immune to pressure and cold. On Pluto, you would stand on frozen ground beneath a black sky. The sun would glow like an intense star, bright enough to cast shadows, yet small enough to remind you of your distance. The landscape around you would be vast and pale. Nitrogen ice plains would stretch toward the horizon. Mountains of water ice would rise in the distance, sharp and rigid in the deep cold. There would be silence, almost absolute silence. As with such a thin atmosphere, if one existed at that moment, sound would barely travel. The wind, if it moved at all, would whisper faintly across frozen terrain. Snow made of nitrogen might fall slowly during certain seasons, settling gently and remaining undisturbed for decades. The temperature would sit near minus 220 degrees Celsius. Your breath would freeze instantly. Any exposed gas would crystallize. Time would feel slow. The sun would move gradually across the sky during Pluto's 6.4 Earth day rotation. Shadows would drift with patience. Nothing would rush. Now imagine shifting to Neptune. You could not stand on Neptune in the same way. There is no solid surface waiting beneath the clouds. Instead, you would float high within the upper atmosphere. Around you, methane clouds would form and dissolve in a dim blue haze. The sun would appear smaller than from Earth, but still brighter than any star. And unlike Pluto, there would not be silence. There would be wind, powerful wind. Jet streams racing at speeds faster than the strongest hurricanes on Earth. Clouds would twist and shear. Dark storm systems might appear in the distance, larger than entire continents. Lightning may flash deep within storm layers. The temperature at the cloud tops would feel nearly as cold as Pluto's surface, around minus 214 degrees Celsius. But beneath you, only a few kilometers down, the temperature would begin to rise. Pressure would increase. Heat from the interior would push upward. On Pluto, cold dominates from surface to core. On Neptune, cold is only the outer boundary. The difference between the two worlds is not simply temperature, it is structure. Pluto offers stillness shaped by deep freeze. Neptune offers turbulence shaped by internal warmth. If you could remain on Pluto for decades, you might witness the slow migration of nitrogen ice from one hemisphere to another. You might see frost recede in one region while accumulating in another. You might observe a faint blue haze form as sunlight warms frozen plains. If you could observe Neptune over decades, you would see storms appear and vanish. You would watch cloud patterns shift with seasonal sunlight changes. You would notice the planet's color subtly evolving as methane and atmospheric chemistry respond to internal and external energy. Cold, in both places, shapes reality. But cold does not eliminate movement. On Pluto, glaciers move millimeter by millimeter. On Neptune, winds race at thousands of kilometers per hour. Both exist under faint sunlight. Both orbit the same star. Both are defined by distance. Yet one feels like frozen stillness, and the other like hidden fire beneath ice. The experience of far is psychological as much as physical. From Pluto, Earth would be invisible without magnification. From Neptune, Earth would blend into the sun's glare. The familiar warmth of our home world would feel impossibly distant. Standing on either world would change your sense of scale. You would realize how small Earth's orbit truly is compared to the vast expanse stretching outward. You would see how the solar system fades gradually, not abruptly. And perhaps you would understand something else. Cold is not emptiness. It is simply low energy. Distance is not isolation. It is simply separation in space. Neptune and Pluto are not forgotten edges of a system. They are active participants in it, one through storms and gravity, the other through resonance and slow geological change. If you could stand there, you would not feel the absence of the sun. You would feel its persistence, faint, distant, but still present. because even at 30 or 40 astronomical units, the sun has not let go. And neither have these worlds. They remain bound in their long orbits, shaped by fading warmth, carrying the memory of their formation billions of years ago. Far, frozen, and still evolving in their own quiet ways. When we began this journey, we asked a simple question: how far and how cold are Neptune and Pluto? By now, the numbers are familiar. 30 astronomical units, 39 astronomical units, minus 214 degrees Celsius, minus 220 degrees Celsius. Light weakened hundreds of times over, years stretching into centuries. But the deeper lesson lies beyond the numbers. Neptune and Pluto teach us that distance is not destiny. Neptune, though far from the sun, remains active. It holds storms powerful enough to reshape cloud systems larger than Earth. It radiates more heat than it receives. It carries within it the leftover energy of planetary birth. It reminds us that even under faint sunlight, internal processes can sustain motion. Pluto, though smaller and colder, remains dynamic in a different way. Its nitrogen glaciers flow slowly. Its atmosphere appears and disappears with orbital rhythm. It may even conceal a subsurface ocean beneath its frozen crust. It shows us that cold does not mean lifeless or static. It simply means energy moves more slowly. Both worlds challenge our assumptions. We might imagine that moving farther from the sun would produce endless decline. Less light, less warmth, less activity. But the reality is more subtle. At extreme distances, the relationship between sunlight and temperature flattens. A difference of billions of kilometers produces only a few degrees of change. Internal heat can matter more than solar flux. Size can matter more than position. Neptune is warmer inside than Pluto despite being only slightly closer to the sun. Pluto is colder at its surface, despite occasionally traveling closer than Neptune. The physics is not intuitive, it is balanced. These far and frozen worlds also teach us about time. Neptune's seasons span 40 years. Pluto's stretch over 60. A human lifetime barely overlaps a fraction of their orbital cycles. To understand them requires patience, measured in generations. They teach us about scale. The warm inner solar system, where oceans flow and forests grow, is only a small region compared to the vast cold beyond Jupiter. Most of the solar system exists in temperatures closer to Neptune and Pluto than to Earth. And yet, those cold regions are not empty voids. They are structured, governed by gravity, shaped by resonance, and marked by slow geological processes. Neptune shapes the Kuiper Belt. Pluto dances in resonance. Even at the frontier of sunlight, order persists. There is something humbling in realizing that for billions of years, Neptune has been turning in blue storms while Earth's continents shifted and life evolved. Pluto has circled the sun only a few dozen times since the dinosaurs walked. Their motions are steady, quiet, and indifferent to our brief history. When we look at Neptune and Pluto, we are looking at endurance. Endurance of cold, endurance of distance, endurance of gravitational rhythm. They are reminders that warmth is not universal. It is a local condition. Most of the cosmos is cold. Most planets orbit in regions far less illuminated than Earth. And yet, even in those regions, complexity thrives. Storms rage under faint sunlight. Ice flows under near-absolute cold. Atmospheres breathe in slow cycles lasting centuries. The far and frozen worlds expand our understanding of habitability and planetary behavior. They force us to reconsider the meaning of active. They show that life-friendly warmth is rare, but planetary dynamism is not. In a sense, Neptune and Pluto serve as boundary markers. not the end of the solar system, but the threshold between relative warmth and deep cold. Beyond them lies an even more distant frontier, stretching thousands of astronomical units outward. And yet, even at 40 astronomical units, the sun still shines, faint but persistent. Its light still defines day and night. Its gravity still binds orbits. Its energy still shapes climate, even if weakly. Far and frozen does not mean forgotten. Neptune continues its 165-year journey around the Sun. Pluto continues its 248-year path, occasionally drifting closer than Neptune, but never colliding. They remain bound by invisible forces, held in balance by physics older than Earth itself. When we step back from the details, the degrees, the distances, the orbital periods, we see something larger. The solar system is not a simple gradient from hot to cold. It is a layered structure where mass, on composition, internal heat, and time interact in complex ways. Neptune and Pluto are not merely distant endpoints. They are chapters in a larger story, a story about how energy spreads through space, how gravity shapes motion, how cold slows processes without stopping them, and how, even at the edge of sunlight, worlds remain alive with quiet change. As Neptune turns in blue storms and Pluto rests in silent ice, both continue their ancient dance around the sun, far from warmth, deep in cold, yet still connected to the same star that warms Earth. And perhaps that is the final insight. No matter how far you travel within this solar system, you are still part of the same story. Bound by the same gravity, illuminated by the same distant sun. Far, frozen, but forever in orbit. On the quiet frontier and the meaning of distance. If you could travel outward through the solar system in a straight line, passing Mars, then Jupiter, then Saturn, then Uranus, you would eventually reach Neptune. And if you continued beyond Neptune, you would find Pluto drifting along its elongated path in the dim outskirts of sunlight. After that, the planets would end. The brightness would fade further, and space would grow darker still. But even there, at 30 and 40 astronomical units, you would not yet be outside the sun's influence. Neptune and Pluto occupy a threshold. They are not merely far from the sun, they are at the point where the character of the solar system changes. Inside their orbits, warmth dominates planetary climate. Outside them, cold becomes the norm. Beyond Pluto lies a region filled with icy remnants, scattered and distant, shaped by gravitational interactions that occurred billions of years ago. And yet, Neptune and Pluto are not boundary stones marking an ending. They are transitional worlds. Neptune is the last of the giant planets. It retains internal heat. It holds onto a thick atmosphere. It generates storms. It creates magnetic fields. It shapes the Kuiper belt with its gravity. It is cold at its surface, but powerful within. Pluto is the first of the dwarf planets in the deep outer belt. It represents a class of icy bodies that are small, fragile, and highly responsive to faint sunlight. It breathes in seasonal cycles. It migrates frost across its surface. It moves in resonance with Neptune in a quiet gravitational dance. Together, they form a bridge between the structured planetary system and the scattered debris field beyond. What makes their cold meaningful is not simply the number of degrees below zero. It is the context. At Earth's orbit, cold is temporary and local, winter passing into spring. At Neptune and Pluto's distances, cold is structural. It defines chemistry. It defines geology. It defines atmosphere. Water behaves differently. Nitrogen becomes rock. Methane becomes frost. Even sunlight itself feels altered. And yet, neither Neptune nor Pluto exists in complete darkness. The sun still rises for them. It still casts shadows. It still defines their years. This persistence of sunlight across billions of kilometers is profound. It means that even at the edge of planetary space, a single star can sustain a coherent system. Far and frozen worlds remain tied to their origin. When we measure Neptune at 30 astronomical units and Pluto at 39 astronomical units, we are quantifying separation. But separation is not detachment. Gravitationally, both are firmly bound. Energetically, both still receive sunlight. Historically, both formed from the same protoplanetary disk that gave rise to Earth. The solar system does not end in silence at Neptune's orbit. It thins, it stretches, it transitions. And in that transition, we see the true meaning of far. Far is not merely a large number of kilometers. Far is the gradual fading of solar dominance. Far is the slowing of seasons. Far is the lengthening of years. Far is the quieting of atmospheres. Far is where internal heat becomes as important as external warmth. Far is where small worlds freeze and large ones retain hidden fire. And frozen is not lifeless. Frozen is slow. Frozen is stable. Frozen is patient. Pluto's nitrogen glaciers may take millennia to shift. Neptune's storms may last years instead of days. Their orbits may span centuries. But change continues. In human terms, these processes feel eternal. In cosmic terms, they are brief. Neptune has completed only about 27 orbits since the formation of the solar system. Pluto has completed fewer than 20. Their long years stretch history thin. And yet, they endure. They endure faint sunlight. They endure extreme cold. They endure gravitational rhythms older than Earth's continents. In contemplating Neptune and Pluto, we confront scale not just of space, but of time and energy. We realize that warmth is local and temporary. And we realize that most of our solar system exists in quiet cold. And we realize that the edge is not empty. It is structured, ordered, and deeply connected to the same star that warms us. Neptune turns beneath blue storms. Pluto drifts over frozen plains. Both continue their silent revolutions. Both remain part of a system defined by gravity and light. And somewhere between warmth and darkness, between inner brightness and outer stillness, the far and frozen worlds continue their patient orbit, reminding us that distance does not erase belonging. They are far, they are cold, but they are still home to the same solar system that gave rise to Earth. If you were to draw a line through the solar system marking where sunlight begins to lose its dominance, that line would pass somewhere near Neptune's orbit. Not because light stops there, but because its influence begins to share power with other forces. Inside that boundary, the sun rules almost completely. Solar radiation drives weather, defines temperature, fuels atmospheric chemistry, and determines climate. But beyond roughly 30 astronomical units, sunlight becomes a secondary actor. It still matters, but it no longer dictates everything. Neptune exists at this boundary. It receives faint sunlight, yet its internal heat shapes its storms more than the sun does. Pluto exists beyond it, where sunlight is so weak that small changes in distance determine whether its atmosphere exists at all. To stand at Neptune's distance is to stand where external energy and internal energy meet in balance. To stand at Pluto's distance is to stand where external energy barely maintains change. And beyond Pluto lies a region where sunlight becomes even more delicate, where icy objects drift in slow arcs, barely warmed at all. This boundary of sunlight is not sharp. It fades gradually. But Neptune and Pluto are its most recognizable markers. When Voyager 2 passed Neptune in 1989, it showed us that even at the edge of solar dominance, planetary activity persists. Storms larger than Earth swirled in deep blue clouds. Winds moved faster than anywhere else in the solar system. When New Horizons passed Pluto in 2015, it revealed nitrogen glaciers and layered hazes in a thin atmosphere. Even in deep freeze, Pluto displayed signs of subtle complexity. These missions taught us something essential. Distance does not equal emptiness. The outer solar system is not a graveyard of frozen relics. It is a frontier of slow physics. Processes occur more quietly, more gradually, but they still occur. The sun's light, though weakened, still arrives. It takes hours to reach Neptune and Pluto, but it arrives consistently every second across billions of kilometers. That continuity of light binds the solar system together. Cold at 30 to 40 astronomical units is severe by Earth standards. But it is not absolute. Absolute cold belongs to deep interstellar space, far beyond the sun's gravitational reach. Neptune and Pluto are cold within a system that still supplies them energy. Their temperatures, around -214 and -220 degrees Celsius, are defined by a balance between faint sunlight and thermal radiation back into space. Their cold is structured by physics, not by isolation. Neptune's upper atmosphere radiates energy efficiently into space, creating its frigid cloud tops. Pluto's surface radiates energy even more directly, freezing nitrogen into solid plains. Yet both remain warmer than the cosmic background because the sun persists. Even at the edge, the solar system holds together. Neptune's gravity organizes the Kuiper belt. Pluto's orbit resonates in harmony. The sun's pull extends far beyond both. When we say far and frozen, we describe a region where warmth is scarce and time is long. But we do not describe abandonment. Neptune and Pluto are not detached from the system. They define its outer structure. They are the final major witnesses to the sun's energy before it thins into darkness. And if we zoom out even further, imagining our solar system from a distant star, Neptune and Pluto would not appear exceptional. Most planetary systems likely possess cold outer regions. Many stars host giant planets orbiting far beyond their inner habitable zones. What feels distant and extreme to us may be common in the galaxy. Perhaps most planets orbit in cold silence. Perhaps warmth like Earth's is the exception. Neptune and Pluto offer perspective not only on our solar system, but on planetary systems everywhere. They show how mass and distance combine to produce diversity. They show how internal heat can defy faint sunlight. They show how small bodies adapt to deep freeze. They show that the outer frontier is not barren. It is simply quieter. And quiet does not mean empty. At 30 to 40 astronomical units, sunlight still defines day and night. Gravity still binds motion. Energy still flows, slowly but persistently. The boundary of sunlight is not a wall. It is a gradient. Neptune stands within it as a distant giant. Pluto drifts slightly beyond as a frozen wanderer. Both continue their orbits in patient silence. And somewhere far inside their paths, Earth spins in warmth, briefly illuminated in a vast system where cold is the rule and light is precious. The far and frozen worlds remind us that distance is relative, that cold is contextual, and that even at the edge of warmth, structure and motion endure. They are not the end of the solar system. They are the beginning of understanding how far light can reach and how much it can still shape, even when it grows faint. They are cold, but they are still home to the same solar system that gave rise to Earth. Why the cold frontier matters. After traveling through distance, temperature, gravity, and time, we return to a deeper question. Why does any of this matter? Why study Neptune and Pluto at all? They are far. They are cold. They are inhospitable to human life. And yet, they may be some of the most important worlds for understanding how planetary systems truly work. Neptune teaches us about energy balance in extreme conditions. It shows that internal heat can persist for billions of years. It demonstrates how atmospheric motion can remain powerful even when sunlight is weak. Its storms challenge our assumptions about what drives weather. Its magnetic field reveals unusual interior structure. Its gravity sculpts the outer solar system. Without Neptune, the Kuiper belt would look different. Pluto's orbit might not be stable. Short-period comets might not follow the paths they do. Neptune is not simply distant, it is architect. Pluto teaches us something equally valuable. Represents a class of small, icy bodies that are likely common throughout the galaxy. It shows how fragile atmospheres behave under faint sunlight. It shows how ice can flow like rock when temperatures fall low enough. It suggests that even tiny worlds might conceal subsurface oceans beneath frozen crusts. Pluto represents resilience in deep freeze. Together, these two worlds illustrate the diversity of outcomes that arise from variations in mass and distance. Move a little farther from the sun, and temperature drops. Shrink the size of a world, and internal heat fades faster. Add a thick atmosphere, and energy is trapped. Remove it, and cold penetrates deeply. The far and frozen frontier is a laboratory. It allows scientists to test models of planetary formation, migration, atmospheric physics, and thermal evolution. And Neptune's outward migration likely reshaped the early solar system. It may have influenced the distribution of small, icy bodies. Some of those bodies may have eventually delivered water to Earth. In that way, the cold frontier may have indirectly influenced the emergence of life in the warm inner system. Pluto and its neighboring dwarf planets help us understand how icy bodies behave under weak stellar radiation. These insights apply not only to our solar system, but to exoplanet systems as well. Many exoplanets discovered so far are Neptune-sized. Some orbit far from their stars. Some may resemble scaled versions of the far and frozen worlds we have explored. By studying Neptune and Pluto, we learn how planets evolve when energy is scarce. And perhaps more importantly, we learn that energy is rarely entirely absent. Even at 40 astronomical units, the sun still shapes climate cycles. Even at -220 degrees Celsius, ice can move. Even under faint sunlight, chemistry continues. Cold slows, but it does not stop. This matters because the universe itself is mostly cold. Most of space exists at temperatures far below those on Earth. Most planets likely orbit in regions where sunlight is weak. If we want to understand planetary systems beyond our own, we must understand how cold worlds behave. Neptune and Pluto are not curiosities. They are representatives. They show us what happens when warmth becomes rare. They show us how structure persists in scarcity. And they show us something about ourselves. We live close to the sun. We live in a narrow band of warmth. We experience rapid seasons and fast weather. Our years are short. Our cycles are quick. But beyond us lies a realm where everything moves more slowly, where storms last years, where seasons last decades, where a single orbit can outlast human history. Studying these distant worlds expands our sense of scale. It reminds us that our place in the solar system is not central in size or distance. It is simply fortunate in energy. Neptune and Pluto continue their silent revolutions, whether we observe them or not. They were cold before humanity existed. They will remain cold long after. And yet, for a brief moment in cosmic time, we have looked outward and understood them. We have measured their distances. We have calculated their temperatures. We have sent spacecraft across billions of kilometers to see their surfaces and storms. That achievement alone reshapes the meaning of far. Distance once meant unreachable, and now it means time and engineering. Cold once meant unknown, now it means measurable. The far and frozen worlds matter because they represent the outer boundary of our immediate understanding. They are close enough to study, yet distant enough to challenge us. And in challenging us, they refine our models of how planetary systems function.